Thank you very much. Good morning, everybody. So this project has been done by my PhD student, close to finish her PhD soon. So Zara, that's what I asked Zara to bring the presentation now. So she will talk, and I'll just jump in when it's needed for the Q&A and the discussion.
Zara, are you just listed under a phone? I don't know if she's listed under a phone number. I don't see her name on the participant list to unmute her. Okay, there we go.
Do you hear me?
Yes, you're good to go now.
Thank you. Thank you. And also you can see my window, right?
Mm-hmm.
Okay. Hello, everyone. I'm Zahra Abbasian, and I'm presenting our technology, which is a separation unit for remediation of Per and Polyfluoroalkyl Substances, known as PFAS. Let me go to the screen. I joined Dr. Foudazi Research Group in 2017 as a PhD student. I have been working in 3 past years on the most recent and a serious contaminant in the water resources, particularly in local area. And before my PhD, I have been working for different industries in the field of unit operation and separation process, in the field of, just to remove soil and water contaminants. Dr. Foudazi has more than 15 years experience in the field of soft matters, including emulsions, foams, and colloidal science. And several researchers have been conducted in his research group to address the existing challenge of agricultural and environmental issues. We received funding for this project from the U.S. Bureau of Reclamation and also New Mexico Water Resources Research Institute. Let's have a quick background on PFAS. PFAS are a group of man-made chemicals which have been produced since 1913 with Teflon invention and used in a non-stick cookware. They also have been used in water repellent and water repellent products and paper product food packaging. PFAS are a main gradient of firefighting foams known as HFFs, produced since 1960. The image on the right-hand side is a conceptual model of PFAS fate and transport, indicating how easily PFAS release to the environment. PFAS emission factory is considered as a one source of air contaminations. Also, the waste stealing from these factories and from the other waste and water and wastewater treatment plant transport PFAS to the soil and groundwater wells. Landfilling of PFAS containing product is another source of contamination of soil and groundwater. And the question here is why, what is the problem with PFAS? PFAS are very persistent in the environment. They are bioaccumulative and they are very toxic even at very low amounts. And unfortunately, they have been, as this map visualized in 2019, water supplies in 49 states in the US have shown PFAS contamination higher than EPA health advisory level, which is 700 grams per liter. New Mexico has been no exception to this national crisis. Groundwater test in 2018 at Cannon Air Force Base in Clovis and Holloman Air Force Base in Alamogordo have shown PFAS contamination higher than EPA advisory level. Dairy business as the most important agriculture in the New Mexico, which creates more than $0.13 billion each year, now is threatened by PFAS contamination. Only in one dairy farm, local dairy farm, 15,000 gallons per day is dumping, and they are planning to exterminate more than like 4,000 cows. In this slide, I have a couple of like shocking statistics about problem associated with PFAS, as 6 million people in the US are exposed to the drinking water contaminated with PFAS in the level higher than EPA advisory level. $12 billion have been estimated cost for drinking water and soil cleanup over a 20-year period. And these numbers get worse when it comes to the people which be affected by PFAS contamination. And it has been estimated 95% of adults in the US have measurable level of PFAS in their blood serum. And $37 to $59 billion have been estimated as the cost of health effect per year in the US. So up to date, several technologies and methods have been employed to remove PFAS from water resources and the soils. Reverse osmosis, ion exchange resin, and activated carbon are three most commonly used methods today. But there is still several limitations have been associated with all these methods. The largest issue which is common in all these three methods is their disposal issues. For example, using RO generate about 20 to 40% of influent as a secondary waste stream, which needs to be disposed of. Also, there is a need to landfilling of single-use resin and also use activated carbons. And also these methods generate a secondary waste stream, again, needs to be discharged. The other greatest challenge associated with these methods is their less effectiveness for short-chain PFAS removal. And also, they usually shows the tendency for absorption of the other molecules in the water stream except PFAS, and this results in their low capacity for PFAS. However, our technology suggests a simple, cost-effective method which only produce 0.5 to 2% of influent as a waste and shows effectiveness for all type of PFAS, both short and long-chain PFAS, but not for other compounds in water. So in this very recent PFAS crisis, we came up with a solution based on the surface active nature of PFAS, which is a cost-effective and eco-friendly method with no chemical used and generate a very low amount of the secondary waste streams. The tray column based on this method is fully customizable, is scalable, and is totally different from the conventional bubbles and fractional columns, which I introduced them in next slide. To design an efficient column, we started with a very fundamental study of physical properties of PFAS, and after a very broad literature review and conducting the required experiment, we finalized the design of our columns, and our technology consists of a separation column, which is a multi-stage injection with low gas holdup. The gas holdup is an indication of the total air volume in the column. The column can be used in a small lab scale as well as large industrial scale with the capacity of 700 liters per minute for liquid and 110 liters per minute for air. Our technology is really a low power consumption method with the power consumption of 1 kilowatt, which comes from one air blower and one water pump. Another great aspect of our technology is generating only 0.52% of influent as a waste stream. Column operation is very simple, which I explain in next slide. But before that, let me just introduce some other technology using bubbling and gas bubbles to remove particles and other contaminants, and describe how they act differently from our method. This picture shows one conventional foam fractionation method, which visually used to remove dissolved colloidal particles from water. Another technology is in situ air sparging method, which is a very routine remedial activity in most of groundwater facility to remove volatile organic materials. As this picture shows, in both technology, gas is injected only in one stage, usually from the bottom of the column or water well. So the small bubble form at the bottom becomes larger and larger while going up through the column, resulting in less particle separation. Also, these two methods usually use a high volume fraction of the gas phase in their system to increase their efficiency. Which this item negatively affect the separation efficiency by increasing the bubble size and also decreasing the residence time of bubble through the well or the column. However, our column, as I mentioned, has several tray equipped with air distributor on each tray. Air distributor form very small bubbles through the water accumulated on each tray. These bubbles move toward to the surface of the water and collect on PFAS because of the amphiphilic nature of the PFAS which they tend to go to the air interface. And at the end, they form a foam layer on top of the water accumulated on top of each train. This foam can be collected from these level control gate and experiencing a low pressure process followed by oxidation process to destroy PFAS molecules. Our column gas holdup is really low. It's less than 20% compared to up to 99% used in conventional foam fractionation and in situ air sparging method. And as I mentioned, this parameter affects negatively contaminant separation efficiency. Here we presented the effect of bubble diameter, gas holdup, and multiple stage on PFAS separation efficiency by using a couple of well-established equations which I presented here. As you can see here, by decreasing the bubble diameter from 200 micrometer to 10 micrometer, PFAS separation efficiency significantly decreased, and it significantly affected PFAS separation efficiency. So we found the optimum and practical bubble diameter based on the bubble rise velocity and the residence time for our system. The second image shows that there is always an optimum for gas holdup. It means that not necessarily a higher gas holdup results in the higher PFAS separation. And we found this optimum for our system. In the last image, we are comparing a single stage column, which is like the conventional foam fraction method, and compare it with our method, which is a multi-stage column. And as it can be seen, a multi-stage system not only decrease the PFAS concentration along the column height to lower level, it also needs air blue air with lower power consumption, and that's because of the lower water pressure head on each tray. So if I want to list some advantage of our technology compared to conventional fractionation and bubble column, I would say increasing mass transfer rate of PFAS to the bubbles because of the higher turbulency of each tray, generating fresh bubbles and unsaturated bubble at elevated height of elevated height of our column compared to the saturated bubble at the same level of the conventional columns. preventing a large bubble formation at that elevated height, which is normally happen in all conventional columns, and lowering the air blower power consumption by at least 1 order of magnitude. And these characteristics all gives us a more flexibility in column design in terms of column geometry. So by this specific design and increasing PFAS absorption on the bubble surface, at the end, we have higher PFAS removal and lower operating costs. Now, according to all these characteristics, there is a wide range of potential application for our technology, including all water and wastewater treatment plants, groundwater treatment facility, and also desalination plants can benefit from our system as a pre-treatment system to reduce the membrane fouling and lowering the operational cost. Military facilities and food packaging companies and all other companies dealing with PFAS in their process are potential application for our technology. Also, it can be used in other food and pharmaceutical process to recycle other type of surfactant and proteins. This graph shows a growing market size of water treatment industries between 2014 and 2025. There is a growth rate of 1 to 2% for annual revenue of remediation industries. However, according to Environmental Business Journal, this growth rate is going to be increased to 2 to 4% because of the emerging issue of PFAS contamination. Also, this chart shows revenue share by end users of PFAS water and wastewater treatment equipment in the US in 2019. Municipal segment presented 70% of this market, and the market is valued about like $100 million in 2019. However, we believe that because of the strong EPA regulation to require different industries to test for PFAS contamination in water resources, we will probably see a massive spending on infrastructure, testing components and treatment equipment in near future. Regarding the current and future status, so far we finalized the column design and we are working on completing the prototype of column. We already filed a non-provisional patent and we received funding for this project. And we are going to initiate our communication with preferably local affected area like groundwater treatment facility in New Mexico. Thank you all for your attention, and I would be happy to ask any question.
Thank you, Zara. We're behind the other parallel sessions, so if we could keep it to a couple of quick questions, and then we can start our final presentation.
This is Beto. I'll jump in and just ask one question, is how are you tracking or keeping tabs on any regulatory or policy initiatives that either hurt or help your case for PFAS remediation?
I will ask Dr. Foudazi just to, if please.
So would you mind, so you are talking about end users, how we can, I mean, control the end users, Paul, or?
Well, you know, PFAS has been around for 50 plus years. Right. Certainly it's a real issue, but you know, unfortunately in some situations, it may be a policy or regulatory mechanism that unlocks the market opportunity to move faster. How are you keeping track of that?
Yeah, that's a great point. I think that's the EPA regulation that Zara is talking about, and what we are discussing. Mainly, what we see is in the agriculture sector, like the milk production. So I think there is a lot of things going on. If EPA cannot control lots of this, the FDA kind of pushes back on things that's related, for example, to milk. So I think we can use that as, or exploit that as an alternative to push the market, if it's the EPA regulation. I work on CO2. I understand your question. I work on CO2 technologies are the same issues. As the president changed, everything changes. So yeah, but FDA, I think, is a strong regulation system to be used for going forward with this technology.